Again. So I've got it recorded and we'll let you continue.
Okay, great. Yeah, so with tracking data, we'll be able to try to assess players' external load. Now, internal load measures are not possible at this moment, but we'll be able to try to assess external load measures from the athletes. But first, we need to do some data cleaning. So I'm sure if you've already used Laurie's scripts, the first thing that he does is he smooths the player velocity traces. And so here what I'm showing you is I'm showing you a graph of a 5-minute period for one particular player, home 5. And this is what his velocity trace looks like before there's any smoothing to take place. And as you can see, I'm going to just split between this slide and the next one. You can see that the smoothing makes the velocity of this player a bit less rigid and a little bit more smooth for all intents and purposes. And so the code for this is listed in sportscience_load.py. If you want to just take a look at what's happening in terms of just calculating the raw velocity and looking at the smooth velocity and seeing the differences. As you can see, the orange one is unsmooth, the green is smooth, and you can see like in places where there are rapid changes of velocity, the function is able to kind of give something a little bit more realistic, especially here. I have no idea what's happening here. It seems like this player changed velocity very quickly, and the smoothing function was able to at least minimize this a little bit. The best way to explain what these different filtering algorithms are doing are using this graphic. So most filters aim to try to create a local polynomial fit across a certain time window, and then estimate the evenly spaced points between them using this local polynomial that it just fits. So I believe what this GIF is doing, its animated visual is doing, is it's taking every 1/10 of a second or so, trying to estimate what the polynomial would look like globally using the local data points, and then from that function, creating the points that it thinks would fit on that polynomial curve. So there's multiple different filters. Here we're using a low order polynomial filter just because our curve is not anything too crazy. And so we can use things between the order of 2 or 3 to be able to, polynomial of order 2 or 3 to be able to fit this sort of data. There are other filters that you use for different data sets, but I think the one that Laurie used is the Savitsky-Boley filter, which is what Will Spearman talked about in one of our earlier Friends of Tracking talks. So that's just the first part. I'm not going to walk through the code of this. It's there in the script if you want to go through it, but I'm not going to go through it for today. So the first thing that we can do is we can take a look at the first external load metric that everyone talks about, which is total distance. And here we are going to output a graph of the distance traveled by each of the players, home and away, and give a different color, whether it's home or away. What you can see here is the home team covered the most distance in terms of the first 2 players, number 5 and number 6. And it's not easy to see here. You'd have to run the script yourself so you can look. Is 5 and 6 were the right winger and the right central midfielder. So one challenge for you, I can do this in R, I'm not the best in Python yet, but one challenge could be potentially to change the size of the circle for each of the players in their starting location based on the distance that they covered. One thing that you might be able to see is you might be able to see in which part of the game, in which part of the field was the game mostly played, or you could see potential hints of the sort of strategy that a team wanted to use. And so that could be a nice little challenge or supplementary exercise that you could do on top of this, is to regraph this pitch using the actual total distances that they did. So I'm just going to quickly go through the code for this one. It's more or less very similar to what Laurie has in his, I think, part 2. But here what we're doing is we are taking the whole list of all the home players that we have from the tracking home data frame. So it gives us an array of all the players that we have that we can then loop over. And the loop within home players is going to look into the tracking home or the home tracking file. And it's going to look at the, sorry, this is the minutes. The speed is going, the distance is going to look over the speed that we're going to calculate. And if we take the integral of our velocity, we'll be able to then get a total distance. So what this is doing is it's dividing it by the number of frames a second, number of frames per second that we have to get rid of the seconds, and then giving us an answer in meters, which we then divide by 1,000 to get us the total distance. So it's pretty straightforward, nothing too complicated here. I've already ran the script, so what you get with at the end is something that has the player names in the index, and then the total distance that each player covered as units in kilometers. And so I don't think that there's any questions that you have here in terms of what the code looks like. It's fairly straightforward to follow. I'm also going to be a little mindful of time, so I want to spend more time with the trickier things. So go back. So the second thing that we can do, and this is also covered in Laurie's part 2, I think it's called delving deeper. So it's part 2 script of EPV, is we can try to look at the different distances that players cover in different speed bands. So here, I think in his script, he mentioned that walking was a certain velocity, jogging, running, and sprinting were different velocities. So running, I think, was between 4 and 7 meters per second. Sprinting was greater than 7. Jogging was 1 to 3 or something like that, so 2 to 4 or something like that, and then walking was anything before that. And so this gives us a better understanding of, okay, well, we know that a player did 10 kilometers, 9 kilometers, whatever. What actually was the distance that he covered in different speed bands? Why is this important? And again, I'm not going to go through the code for this one because it's listed in Laurie's part 2, and I just simply reuse the same code in the script that you see in the files that I put on the GitHub. And so why is this important? It's important because when a player is operating at different velocities, whether it's low, medium, or high, the sort of lactate that their muscles are producing changes depending on, like I said, the efficiency of this player or the fitness of this player. And so if a particular player is not so fit, as they're approaching higher velocities, they'll be having more lactate within their blood, which means it's going to be harder for them to produce more work or produce more power. And so they'll be fatigued much quicker, and they will need a little bit more time to recover before they're able to perform at maximal capacity again. So what you see here is you see a blood lactate curve. On the x-axis is velocity, on the y-axis is the reading or the value of their blood lactate. And typically what we do is we do a test with the athletes to have them run at certain speed bands. So we will place 2 cones apart, and they need to get from one cone to the next cone within a certain number of seconds. And so this will allow us to do a testing of their blood lactate at 3 meters per second when they're traveling, or when they're traveling at 4 meters per second, when they're traveling at 5 or 6 or something like that. And what this lets us do is it lets us create a nonlinear regression to then model where exactly is there an inflection point or the elbow point of this player's blood lactate curve. And this can help us maybe move towards something that's a bit more individualized. So here in Laurie's code, you see that the concept of walking, jogging, running, and sprinting were based off of absolute speed thresholds, regardless of who the athlete was. Sprinting was the same, running was the same, so on and so forth. But if you ever watch football, you know that a winger, right winger, left winger probably has a better sprinting capacity than someone who's a central back or center back. And so these two players should actually have individualized speed thresholds, because a center back that's running at 5 meters per second is definitely doing much more, it's giving much more internal load to that player than, let's say, a winger traveling at 5 meters per second, simply because of the demands of that position and also the type of body type required to be able to play that kind of position. And so these sort of blood lactate curves help us get to more individualized speed thresholds and lets us understand what does it actually mean for a particular player to do a sprint from an internal load method, not just using an external metric. Can't necessarily show anything here because it's highly personal data to the athlete, but hopefully you get the concept. We're simply just fitting a nonlinear regression, finding its inflection point, and then from that we can then create different sort of segments for the player's individualized speed threshold. So the first concept that we'll move through with the code and the images is accelerations and decelerations. So distance is more of a physiological external load. Accelerations and decelerations are the sort of forces that you're going to be applying on the ground based on the mechanical state of your body. So many people tend to see this as a biomechanical aspect of external load. But what we end up seeing in this graph is we see that the acceleration-deceleration ratio, which is the number of accelerations that the player made divided by the number of decelerations that the player made, they can be completely two different values, even though the distance that they covered were relatively very similar. This is very important because it shows that not all distances are created equal. Two players could have both traveled the same amount of distance, but one player could have done much more accelerations than another player. And it provides a sports scientist with a good understanding of knowing, okay, if he did many more accelerations, it was then this sort of load from a biomechanical perspective. Again, I'm not an expert in biomechanics, so I can't go more than that. This is just sort of data that we give them. But it lets the expert or the domain knowledge experts around biomechanics or sports scientists understand better how or what was the nature of this distance that they covered. And so we will go through the code for this one because I think it's a good one to go through. And so basically what we're doing is I've set the max acceleration to 6 meters per second squared within all of our GPS readings that we have internally. It seems that most players are not moving past 6, and if it's past 6, it seems like it's an outlier. So if you're going to ask why did I choose 6, it's just something that we have seen from the data that we collect internally for the last 3 years. So to calculate an acceleration, I'm thinking an acceleration is going to be moving either plus or negative 2 meters per second squared. What we do is we create a dictionary first, and we're going to loop through all of the players in our array of home players. First, we're going to calculate the acceleration of that particular player. If the acceleration from the tracking data is going to be above the 6 meters per second squared that we have, I'm just going to assign it to the value of NA. And then I will segment out the different accelerations that I have based on high and low. If it was above plus or minus 2 meters per second squared or below plus or minus 2 meters per second squared. The 2 comes from a heuristic that's provided by our GPS provider, Catapult, that says anything above 2 is typically considered a high acceleration. Again, this is very up to debate, and there's a lot of research around this in terms of you can create individualized acceleration thresholds as well. But for right now, for this purpose, we're using just 2 for something heuristic. And this piece of code is creating what I call an acceleration group. And so an acceleration group is taking a look at if there are consecutive frames within the tracking data to show that someone is actually sustaining an acceleration above +2 or below -2 meters per second. So this column name here, home, the player name, which would be like 5 or 6, so home 5 acceleration G, is giving us all the different groups. So if we take a look for one player, go into tracking home. We see what it looks like for a particular player. We see that here it's a group of low, so it's going to say the same, it's going to say the same. And then we see that the player has now shifted into a high acceleration that's above 2 meters per second. And then now we've listed this as its own group. So this is a acceleration group 2. Acceleration group 2 has type high with these values above 2. And then then it shifts back out of 2 into 3 again. And then when we see 4, we have a deceleration that's happening below -2 meters per second squared. This sort of grouping then allows us to loop through each of the groups. It gives us a sense of the duration of that acceleration, if it was an acceleration or deceleration, and then allows us to produce a data frame like this one. So we have for each player, we know what the group was, group 1, 2, 3, whatever, and we can figure out if it was an acceleration or deceleration. And here we're only just looking at the groups that were considered high. So they were accelerations happening at +2 meters per second squared. And then we calculate a box plot for this data for the duration. And what we see is we can see that most of the durations of these accelerations are happening less than half a second. So just for explanation purposes or this lecture's purpose, I just set a threshold of 3/4 of a second in terms of what I'm going to consider an acceleration or not. This gives me the true count of accelerations that people do. So I can then loop through this data frame here, which is a subset of all the high accelerations, and get a count, get an official count. So if I go now into home summary, I have a ratio score for each of the players because I've defined this here in terms of the number of accelerations that they did that were above or minus or below 2 meters per second squared, whether it was an acceleration or deceleration. It was sustained for either 3/4 of a second or greater. And that's how I'm going to create a count or assign that acceleration or deceleration to an athlete. So that's what that piece of code is doing between lines 178 and 214. And so this then allows us to produce a graph like this and shows us kind of the complementary nature of the physiological external load, which was the distance that the player covered, but then also the biomechanical load that the player took on, showing that, here's a good example, player 10 and player 8 covered more or less similar distances, but their acceleration deceleration profiles were different. The challenge that you guys are going to do starting tomorrow, or will be assigned to tomorrow, will be something around acceleration deceleration ratios. So one other concept which we can take a look at is metabolic power. I'm going to provide these slides to David, and he can give this out to people so that you can take a look at this link here to the bottom right. It shows what are the pitfalls of using this metric, especially when it comes to using it for elite athletes. But the idea here is we want to try to understand what are the energy demands of a player. If we can understand what is the energy output of a player over time, we might be able to get a sense of when is the ideal time for a substitution, or potentially what are the pacing strategies that the player is using. So here, metabolic power, it's defined as a function of a player's speed and acceleration. Effectively, I'll send the link here in the chat for people to do some reading on it. It effectively assumes that if you are running at varying changes of velocity using kinetic energy to translate your body into producing faster velocity or moving at a faster velocity, it's going to be requiring more energy for you to do this change in. Sorry, I explained that very poorly. What I meant to say was, if you're moving in higher velocity, the angle upon which you run relative to the ground changes. And when the angle upon which you run to the ground changes, the amount of force that you're exerting upon the ground increases, which means you need to then increase your energy outputs to be able to account for this change in running angle relative to the ground. So there's research that's been done around trying to produce these sorts of graphs or a metric to kind of estimate energetic demands of athletes so that we can understand when fatigue sets in. So you can think of this as time series data, and with time series data, we can apply something called ChangePoint Detection. And ChangePoint Detection is a type of algorithm that uses a cost function or a search method. Here we're using binary segmentation. And what this does is it tries to find a moment in time where the points to the right and the points to the left are different based on likelihood ratio test of the cost function that's used for the algorithm. Here I'm just using the ruptures package in Python. So the documentation there, I think, is using a standard linear least squares cost function. And so here what we see is binary segmentation is allowing us to define the number of breakpoints. We can use this if we know the number of breakpoints. So here we want to just use one because we want to identify the moment in this player's time series where we think it could be a good time for this person to be substituted, as the power output or the energy output of this player has started to reduce compared to what's to the left. Another thing that we can do is we can use something called pruned exact linear time, which translates to PELT up here. And this is used if we don't know how many breakpoints there are. And this could be a good method for being able to identify the pacing strategy of the player. So the blues and the reds are just different segments that the algorithm picked up on in different 5-minute intervals. And it allows us to maybe get a sense of if a player was doing more work during this time or expending more energy during this 5-minute segment, less energy during this 5-minute segment. And this sort of pacing could be relative to the player actually needing to recover from acute fatigue, or it could be based on the tactical demand. So there's a lot more complexity that needs to be explored from just this graph, but it gives us a sense of how much energy is the player exerting in different sections of the game. And I think this player played the whole match, so you're seeing something for the whole match. So we'll go through this code in Python. And so what we're doing here is I first needed to define this function to split the column names, so that's not doing anything else. And I defined a function for calculating metabolic cost. And so metabolic cost, you can find the link that I just gave to you through the chat. You can also find it in the code if you want to read more about where I've derived these equations from. And so what I'm doing is I'm taking all the different player IDs that we have. In this case, I'm just looking at one player to do an example. I could implement this as a function, but for the lecture purpose, I'm just going to look at one player. And here, I'm going to calculate the metabolic cost for this player across his entire tracking data set that we have for him. And the metabolic cost is then multiplied by speed to give us the proper units for power. So that's what's happening here. The next line is we're going to do a rolling 5-minute window, 5-minute sum for this player's power outputs. And so this is just doing a rolling sum for that. And then we get a graph that looks like the one that you saw on the slides. So this is a person's 5-minute rolling window for their power outputs for the course of the match. And here we're going to use the ruptures package. I've imported it as package RPT. I'm going to look at the 5 minutes after. I'm not going to look at the first 5 minutes as he's moving toward, as I'm just getting the rolling window started. And I'm going to look at the 5 minutes up until the 90th minute for the results. In this scenario, we know the number of breakpoints. We're only looking for the location and time for this player where we think it might be a good idea to substitute him purely from a fatigue perspective. And then this ends up giving us the graph that you see here. The second method that we use is PELT, which is then called using the RPT PELT method. And here we do not know the number of breakpoints, but in the Python documentation, I believe here, let's see. And the Python documentation provides us with a heuristic for what we can use as the penalty. And the penalty is effectively a score that the likelihood ratio test needs to be greater than between the points to the left and the points to the right for the change point to actually be considered. Where exactly is? I'll find the documentation properly and send it. But the penalty that I'm using is based off of a heuristic that was provided in the Python documentation. And then this provides us with this graph here. So it's identified these as the different breakpoints. Potential supplementary exercise from this could be to play around with the different sort of search methods that the ruptures package in Python has to see how the change points change if you change your penalty. So if you make your penalty not so strict, you'll have way more change points. If you make your penalty much stricter, obviously, it'll be harder for the algorithm to detect where changes actually happen. But the whole goal of being able to use ChangePoint detection when we don't know the number of breakpoints is to try to identify different segments in the game where we think players are playing above their match average or players are playing below their match average. And this is a concept that I will really come back to towards the end. So moving on, there is a concept, I'm just going to play this video quickly to show you what I mean, is that we're going to see Gareth Bale make a very intense sprint. And so one of the things is that before the use of data science, or before the use of programming in sports science, the only sort of questions that people asked were, what was the total distance that someone did? What was the distance per minute someone did? Now what we can look at is we can look at what was the 1 minute most intense moment that a player had to go through. Because the sort of data that we get from the GPS provider comes at 10 Hertz. And so we can now calculate more granular understandings of external load. So here what you see is you see what my colleague calls a sequence of peak intensity. And that's effectively a 1 minute period where someone had to travel above a certain threshold. and we see the 5 minutes after. And so the red bar is showing the number of meters that a player covered based on the position that they were. And then the gray bars are just showing the meters that they're covering in high speed after those 5 minutes. And so what you can see is, you can see for most parts, they are less than this line here. And this line is what the match average was for this position. So per minute, a center defender is usually covering 1.1 meters in high speed per minute. For a central midfielder, it's 1.664. So one of the first questions that you would ask even before you do any sort of modeling is you would want to understand, is this actually statistically significant? Is the distance that they cover 5 minutes after a sequence of peak intensity, is it actually statistically lesser than the match average? So this image is kind of priming us for a question that we will answer in the following slide. And it's probably one of the first questions that a lot of sports scientists want to know is differences between different samples, differences within subjects and between subjects. And so we do perform a lot of different sort of analysis of variance tests. And since analysis of variance or paired t-tests are just a special case of linear mixed models, what we generally use a lot of the time are these generalized linear mixed models. And so this image kind of helps paint the question. Here what you see is training periodization, and you see that what the sprint distance was, or what we saw, was that within Benfica, is that we didn't really prepare our players that well when it comes to sequences of peak intensity. So we do see that players are not performing up to match average after doing a 5 minute intense sprint, or after doing a 1 minute intense sprint. And potentially it could be because during the training sessions, whenever they do their sequence of peak intensity, their 1 minute sequence of peak intensity, it's only really 33%, 37, 48% of what they get exposed to during a match. Only the fullbacks do we really get anywhere close to what they get exposed to during a match. So perhaps what we could do with a different training intervention, if we actually provide training drills where they're needing to sprint more at higher velocities, we might actually be able to allow players to still perform at high velocity even after they've performed a 1 minute curve. And so being able to use linear mixed models to look at the pre-intervention and post-intervention allows us to actually measure the difference of our players able to recover quicker. So to get into that linear mixed model, what we're doing is we're going to first calculate the sequences of peak intensity in Python, and then we're going to calculate what the minutes after that sequence of peak intensity looked like. After doing that, we're going to compare that with the match average of the distance per minute that that player normally covers, and then do a subtraction between what they covered the minute after their sequence of peak intensity compared to their average distance per minute. So what you see here on the graph to the left is a violin plot of the difference between what they covered a minute after their sequence of peak intensity and the distance per minute that they did as a match average. And you can visually see that they definitely are producing less than their match average. And here on the right is the output of the linear mixed model, which we will go into the code for. But effectively what it's showing us is it's showing us what is the global mean, what we call the fixed coefficient. And the global mean is showing us that it's 21 meters less than what a player is normally covering on average distance per minute wise. And then we're using the player as the random effect, or as the way we're going to handle the between and within subject variability to give us these confidence intervals based on the standard error. So we do see that within both extremities of our confidence interval, 95% confidence interval, we are between -27 and -15, which lets us know that, okay, for sure, it is statistically significant that the minute after a sequence of peak intensity, players are fatigued and they're not able to produce a match average performance from a physical output point of view. So the formula goes, this is a very simple, the most basic linear model, the linear mix model that you can create. It's effectively saying that we're going to try to create a relationship between the difference between the 1 minute after a sequence of peak intensity and the distance per minute to its global coefficient, which is -21. And I'll show you where we get this from. And we're going to account for the variance in differences based off of different players. And this is because we know that the data is not independent. Each player definitely has its own fatigue profile. So after doing a sequence of peak intensity, they're going to respond to it in their own way. So if we have multiple recordings of a particular player, we should have some sort of within subject variability, but that within subject variability of one player is going to be different than between players. And so because different players have different responses to doing a lot of work. And so if we go into the code.
Can I just ask, Suds, maybe there isn't an answer to this, but how can you be sure that it isn't the case that after you've had a high intensity bout, there isn't another high intensity bout typically? So that it's nothing to do with a physiological thing that they can't get up to those speeds. It's just that they're less often required to, because often the ball has gone out for a corner after like something like that. Either the ball will have gone in the goal, gone out for a corner, something like that.
Yeah, no, it's a good question. So the way that we have handled, it's a very good question. The way that we've handled this is that the test that we did not for the lecture, but the test that we've done at Benfica is we wanted to look at 5-minute intervals where the ball is still kept into play. And we're looking at 2 seasons worth of data, and our assumption is that if we're looking at this much, while we're only looking at moments where the ball is kept into play, even after someone has done their intense bout, we can assume that the player could at least perform up to match average if they needed to. So we look at sometime in the paper that my friend and I republished, we look at even 2-minute, 3-minute rolling windows where players might need to perform a secondary bout, perform 1 minute of intense movement, maybe 20 seconds of rest, and then perform something again. But we do see that after they perform the first one, the nature of the second bout that they do in quick succession is not as strong. So it's a good question. It definitely is not, it definitely would have to be an additional random parameter, a random effect that we could add into a model, which could be potentially a categorical variable that says, was the play happening near that player or not, while this person was recovering from their intense bout. So you ask a good question, but for now we're just assuming that if we have enough data and if we're looking at moments where the ball did not go out of play for a corner or did not go out of play for a goal, this player should be able to perform at least match average. But it's a good question because let's imagine that the ball is actually happening in the complete opposite area of the field from that player, so he does not have to perform at even match average. So yeah, it's a good question. But I think the best way to answer it would be to add another fixed effect parameter, which would allow us to account for the fact that we can look at moments when the ball was still kept into play after someone did a bout, and the ball is around his zone.
Yeah, I think one simpler way even would just be to leave a maybe 1 or 2 minute window. So you do 5 minutes either side, but you shift it forward so you don't do immediate 2 minutes. Because we've been thinking a lot in this course about the way that football's random, which you can use in this thing. So
okay, yes, that's a good point.
you're unlikely to have those types of correlations again.
So the study that we did for high-speed running was that we saw that even after 1, 2, 3, 4, 5, so even after 5 minutes, the player was still below his match average. Where we made the assumption of, okay, we're just keeping the study to the ball was kept into play after the person made an intense bout, and we're looking at the 5 minutes after. Is it consistently always below the match average? In this example, I'm just looking at the minute after, but I think you're right. Only looking at 1 minute is too random. It's too variable because a lot of things could be happening on the pitch.
Anyway, I'll let you get on.
So if we go into the code for this one, I'm not going to run it because this takes some time to run, but what we're doing is we're looking at the speed of the player. We're going to take a 1 minute rolling window. We're going to use a function within SciPy called signal find peaks. What find peaks does is it's going to let us identify all of the different It's going to help us identify all of the different peaks within our graph that are happening 1 minute before, 1 minute after the last peak. So this algorithm would have found a peak here, potentially a peak here, peak here, like that. And I'm just going to take the top 3 peaks. The reason why I'm doing this is because for this lecture's purpose, I needed to have enough of a sample size to do a very simple linear mix model. And if I just would have looked at the highest, most intense bout, then I wouldn't have been able to produce a model that actually converged. And so we then calculate the minute after using this script here, or this for loop here, for each of the 3 peaks that we identify for each player, calculate the minute after for this player based on the index of where that peak happened. So that's what this line of code is doing. And the rest is, the second half of this loop is doing this for the high speed distance where someone is traveling above 5 meters per second. We then get to a point of adding this into the summary is just creating a distance per minute for that player. And then we are creating a data frame that's going to contain for each player what was the value of their sequence of peak intensity, what did they do the minute after, what was their distance per minute, and then the difference between them. So that's what these lines of code are doing. Doing it for the away players as well, so I have a bigger sample size, and then we end up with something called HSD full. And HSD full looks like for each player, we know what the type of sequence of peak intensity it was, total distance or the distance traveled above 5 meters per second. What was the actual value of it? What did they cover a minute after in terms of total distance? What was their distance per minute for that match? And the difference. So that's what these lines of code do regarding SPI. And what we do use is we use something from SNF. SNF is from stats models. So we import the mixed model functionality from stats models to be able to produce our mixed model that looks like this. And here we see the same output that we get from our presentation here. And what we see is the intercept, the coefficient of the intercept is negative 21.033. Since we are not relating the difference to another continuous variable like we could have for SPI or something like that, we're just relating it effectively to itself. We see that the coefficient, the global coefficient of negative 21.033 is in fact the global mean of if I just look at all of the differences between the minute after and the distance per minute for the whole game. given the high-speed distance for this data frame. And so that's where we're getting this from. And then our confidence intervals are based off of the between subject variability that we get from the different players that we use. So you would see if you tested this out, if you tried to run a t-test, or if you tried to run a simple t-test or a simple ANOVA and tried to look at the sort of standard error that you got along with the confidence intervals, you'd see that they're slightly different. And that's because the way that the mixed model pools variance for grouping together random effects, in our case, we're using player, it's different than if we had independent data samples. So typically mixed models are used for longitudinal analysis and trying to assess differences between groups where you have repeated measures. Great, okay. The last part is going to look at just the relationship between EPV and external load. I already saw that timing-wise I'm a little bit over. So this code here you can take a look at in EPV. What I'm doing is I'm just taking Laurie's code for understanding what is the total EPV of a possession using all of the passes in that possession, and then creating a simple linear regression between the actual EPV and the distance that they cover.
I think actually, Suds, I haven't even covered EPV in the lectures yet. That will be next week's lecture.
Okay.
So I think actually what we can do is we can come back to that later, or I'll come back to that next week.
Okay, cool. Yep.
If you send me that slide, I'll use that slide next week to have a look at that, and you and I can talk about exactly the conclusions there.
Okay, cool. Now we'll skip this for now. Then that's it. I will look at questions right now, but effectively you guys will have 3 challenges starting tomorrow. One of the challenges will be based off of the sports science module. I think I'm going to talk to David about it, but it'll be something around clustering different players based on their acceleration, deceleration profiles and the distance that they cover, to see if you can find any patterns regarding the positions that they play. So maybe if we look at the physiological external load and the biomechanical external load of a particular player, and if we cluster this together, do certain cluster groups, do they correspond to positions that players play on the field? So the challenge would be based on either confirming that hypothesis or rejecting that hypothesis. And I'm just going to say thank you in multiple different languages, because I know there's a lot of people from around the world who signed up for this course, and that's it.
Thank you very much, Suds. We'll just, if anyone has got a few extra questions, if you can hang around for 3 or 4 minutes, then you're very welcome to pose them. Otherwise, the official part of the lecture is finished. And I'll just say, yes, maybe I should just say a bit of things. Everybody in the course, you should have seen the announcement now, which outlines all the important steps for the last part of the course. As Suds mentioned there, one part of that will be an exercise related to today's lecture. I will send that out on Wednesday morning. But tutorial, so Wednesday morning I'll send out the exercise, and tutorial as usual on Thursday in the groups as usual, and then we'll go through the exercise. I've said that Thursday tutorial, that's obligatory, because I want everyone to come, because you're going to do these things as a group together. But please come along to that. I don't think the people who are in this chat will have any problem. That's the times are as usual: 2 o'clock group tutorial team 1, 2:30 tutorial group 2, 3 o'clock tutorial group 4, and 3:30 tutorial group 5. There's no tutorial group 3. Great. I'll just ask one thing. I would like to go back to a couple of the questions that came up, because there was questions about both about what you do if you're using, for example, artificial grass when it's raining, all of those external things. Do you do any type of correction for them at present?
At the moment, no, but you're totally right, because the amount of ground force that a player is exerting using artificial grass is different. I've seen companies before that produce some sort of sensors that allow us to know what is the softness or the hardness of the pitch, which would then allow us to do a very rough modeling of the sort of force that a player needs to exert, but we don't do anything at the moment with that. It is a good point to raise. Again, when sport, regarding most of the things in sports science, it's like David pointed out in that mixed model, there's a lot of different sort of categorical, or there's a lot of different variables that we're probably not accounting for to be able to explain the variance and things that we see better. So a lot of these models are not perfect in nature. A lot of them just give us heuristics that we can work with. But yeah, there's definitely a lot more space to explore.
And quite a few questions came up about tactical things. I mean, Vinny suggested that you could instruct your players to reserve power to wear them out on the 70th minute. I'm not sure that's practical with football players, but maybe you could comment on that.
No, so it's a good point. So two things I'd like to point out. I'll go back to this slide here. Two things I'd like to point out is one thing that we saw with our study that we did regarding the sequences of peak intensity was we saw that using a ratio test, we saw that it didn't really matter when in time, whether the sequence in peak intensity happened in the first 15 minutes, the second 15 minutes, the last 15 minutes. Players always pace themselves in a way that they leave enough in the tank to always do an intense bout if they need to. Teams could technically be instructed to do this. And so I think what is something that's interesting to look at, if you guys have time, is to play around with ChangePoint detection and look at where all of the different pacing segments happen for a team, where teams are pacing upward together or teams are pacing downward together. What I mean by upward or downward is above their match average or below their match average. And then you might be able to find moments in the game where an entire team or certain subsets of that team, let's say 4 or 5 players in that team, are all performing above their match average. And you might find some interesting relationships to the sort of chances that they created, even if you use an XG model instead of an EPV model. You might find some interesting things in terms of when you have a large enough subset of your team pacing upward or above match average. You find your quality of your possession to be better. Now, do teams just instruct them to do that? In reality, that's very hard to do. Coaches want their players to be playing very intensely throughout the entire match, and it's up to the player to figure out how to best pace themselves. I don't know how to find it.
I think it's always considered in coaching very dangerous to tell players anything about, like, you know, taking it easy the first 30 minutes or something like that, because what do you do if 2 goals go in those 30 minutes and you've been, those types of things are very difficult to increase intensity at various parts.
But it is true. You can, if imagine we had GPS data live. You don't have this at the moment, but what I would do is I would look at the pacing strategy. So ChangePoint detection comes in either two ways, offline or online. And online can be used to assess change points in real time.
Yeah.
And so what I would do is I would try to identify, are there enough of our team actually pacing above average? And if we are, instruct the team to attack during this phase. But if I see that 5 or 6 of our players are in the same time period pacing below their match average, the focus would be on defensive organization. And so if we had this data live, it would be amazing to use, because that's exactly what I would use it for.
Mark has a good point there, that if you pace down, then your opponent will pace down as well, so they won't get fatigued. And also, you often see that one tactic that is used, of course, is when you do have a 1-0 or a 2-0, especially a 2-0 lead, you just pace down in order for it to make it harder for the team to get up to a good pace, because it's a natural thing you see at all levels of football, that you play at the pace your opponents are playing at. It's a sort of social thing, despite all the pressure and so on, especially now in the Corona team where there's no audience there or crowd cheering you on. Then you just reduce your pace down to whatever your opponents are playing.
It's an interesting point. I would create a hypothesis to the group to say that definitely there is herd mentality of if you're going to slow down, then the opponent's going to slow down. However, for an opponent to create meaningful chances, there will be moments in their possessions where they do need to accelerate into higher velocities.
Mm.
And so this is now very, yeah, you would then need to try to get them and bait them into doing that. And so if I knew that, let's say this 5 minute period, we are mainly pacing below average, the goal would be then to try to organize defensively in a way to attempt the other team to retain the ball. And through them retaining the ball, they would then need to try to find good opportunities, and to trying to find good opportunities, they would invariably have moments in their possessions where they would have to accelerate the ball, because what you may find is you may find the relationship between quality possessions and distance covered at velocities, which will be the slide that I'll talk to David about later, increases when teams are actually moving at a faster rate. So yeah, this game is just there's too much variability in this game to analyze everything properly.
Great. Okay. Thanks a lot again. And